Okay, so in this video, we're going to continue talking about Kirchoff's circuit laws. We talked about these laws in the last video, and these are basically like the Newton's laws of circuits. Okay, so these two laws are fundamental to being able to solve circuit problems. And the two laws are the junction rule and the loop rule. And so the junction rule basically says that all of the current going into a junction has to flow out of that junction. That's a statement of the conservation of charge we talked about in the last video. And then the loop rule, which is the more important of the two, basically says that if you add up all the voltages around any closed loop um, in a circuit, they have to add to be zero. And by closed loop, I basically mean you pick any point you want along the circuit, and if you can draw it without picking up your pen, that's a closed loop. Okay, so you add up all the voltages. Some of them are going to be positive, some of them are going to be negative, but they all have to add to be zero. And we talked about that in the last video. Okay, so in this video, we're going to get into doing some examples with Kirchhoff's laws. But all three of these big equations, by the way, are given in the data booklet. Okay, so I believe this is where we left off last class. All right, so just to see a simple example of Kirchhoff's junction law, the first law, that says the total current going into a junction must equal the total current leaving that same junction. Okay, so that's given in the data booklet as sigma I equals 0. Basically, the sum of the currents into a junction has to equal 0. And just to give you a really simple example of that, here we um, have some wire and we have 5 amperes going into a junction. Now remember, a junction is just a point in a circuit where the current can split. Okay, and so if you imagine like a pipe carrying water and then the pipe splits into two, the water either goes into one side of the pipe or it goes into the other side of the pipe. It just can't go nowhere. Okay, so if we have 5 amperes going into this junction, Kirchhoff's junction rule says we had to have 5 amperes coming out, okay, which we do. See, we have 3 amperes going this way, we have 2 amperes going that way. Okay, 5 is equal to 3 plus 2. Okay, so the current going into the junction is equal to the current going out of the junction. Okay, which seems really common sense, but you can use the junction rule to figure out, like, if I know this much current is going into the junction, and let's say I didn't know one of these two other currents, I could, just subtract that to figure out the missing current. All right, and here you see something similar um, on the right side, just another simple example of the junction rule. Okay, so we have Kirchhoff's junction rule. And then let's talk about the loop rule. Now, there's some sign conventions that you need to be aware of when you're applying the loop rule, because basically what you're adding is you're adding voltages. Okay, if you're in a situation where you're going up from a lower potential to a higher potential, that would be a positive voltage. Okay, if you're going down in potential, if there is a potential drop, then you would add that as a negative because you're losing potential, you're losing voltage. All right, and so be aware of that sign convention. When you're going across a resistor in the same direction of the current, you treat that as a voltage drop. Okay, so you add that as a negative voltage because you're going down in energy because that energy is being used in the load. Okay, likewise, when you're going across a resistor opposite the direction of the current, you're basically going up in potential. Okay, when you're looking at a cell or a battery, when you go from the negative side of the battery to the positive side of the battery, you're going up in potential, you're going up in voltage, that's a positive voltage. And then when you go from the positive side to the negative side, that's a negative voltage. Okay, so make sure you have these in your notes so you understand the sign conventions in applying the loop rule. Okay, now just to give you a really easy example of the loop rule in action, here's how you might apply the loop rule. Okay, so I want to make a loop. Okay, let's take a look at the circuit on the left to begin with. It does not matter where I start the loop because the circuit is so simple, it really doesn't matter. But let's say I put my pen right here. Okay, a closed loop is a loop where I draw until I end up back where I started. And Kirchhoff's loop rule says that I'm going to add up all the voltages along my path and they all have to equal 0 at the end. Okay, so let's say I go this way. Now there's nothing that says I have to go this way because the loop rule works for any loop. Doesn't matter. But let's say I go this way. When I go from this negative terminal to the positive terminal, I'm going up in potential. Okay, I'm going up by 12 volts. Okay, so I'm adding up the voltages as I go, and that would be plus 12 volts. Now, there's a resistor. Okay, there's going to be a voltage drop when I go across the resistor. I do want to point out, by the way, that because of how the circuit is set up, the current is going to be flowing counterclockwise because the side of the cell is positive, so the current is going counterclockwise. So when you go across a resistor in the same direction of the current, that means there is a drop in voltage. Okay, so I'm going to go down in voltage right here. Now, how many volts am I losing? I don't know. Um, if I had more information, I could calculate it because a voltage drop is given by V equals IR. So if I knew I and I knew R, I could calculate what that was. But for the time being, let's say I don't know. And then I keep going around my loop. Okay, I come to another resistor. I'm still going in the same direction as the current, which means I'm going to have a voltage drop, and it's going to drop by 8 volts. So I do minus 8 volts, and the second you get back to where you started, the loop rule is over, and whatever you've added up along the way, that now has to be set equal to 0. All right, well, I now know, just from common math, what has to go in this blank. That has to be 4. Okay, so in other words, there was a voltage drop of 4 volts there, and I know that because the loop rule has to be met. Okay, if I went up 12 volts, in order to get back to where I started, I had to go down 12 volts by the end. Okay, so if I went down 8 volts here, that left 4 volts for me to go down there. Okay, and I'm not going to do the same thing for this other loop, but hopefully you start to see how that works. Okay, so this is basically um, how the loop rule works. Here you can see the answer for the one on the right. Here it looks like a loop was made starting down here, or starting over here. They went up 12 volts, and then they went down 2. They went down 9 right here because they went from positive to negative, so that's negative 9 volts. And then they went down another 1 volt. Okay, and it all has to add to 0 at the end. Okay, so now that you hopefully start to see the general principle, let's see what actual problems look like when you know Kirchoff's two laws. Okay, so here's a problem, and let's say I'm given the task of finding I1 and finding I2. Okay, so I'm going to apply what I know about Kirchoff's two laws. Now, I'm told that there's a cell right here and that the voltage on the cell is 3 volts. I'm also shown that the current is going clockwise, which I would know anyway from the diagram, and that this current right here is 0.18 amperes. Okay, so the current 0.18 amperes is the same until it gets right here. Right here, where I'm drawing this dot, that is a junction. That is a pathway where the current can split. So I don't know what I1 is and I don't know what I2 is, but I know because of the junction rule that if I have 0.18 amperes going in, I1 plus I2 has to add to be that value. Okay, and so this first equation comes from the junction rule. Now, can I do anything with this equation? No, because it's one equation and two unknowns, and I can't do anything about that. Okay, so now I'm going to go to the loop rule, which tends to be the more powerful of the two. Now I'm going to apply the loop rule. And the nice thing about the loop rule is it really makes no difference what loop you make, it always has to work. I always like to go with the current if possible just because I find it easier. And so I'm going to make a couple loops. And in fact, I'm going to make more loops than I actually need just to show you how it works. Okay, so I'm going to start down here, just, I don't know, because, and I'm going to go up to begin with. All right, and I'm going to add up all the voltages I see along the way. Here I'm going from the negative side to the positive side of the cell, so that is going up by 3 volts. And I keep going. There's no voltage drop along a wire, so I'm not adding anything yet. And now I have a choice. And just to start off with, I'm going to go down the first loop. Okay, so here I'm going to go down in potential. Okay, now the voltage drop, remember, is given by V equals I times R. Now, I don't know what I is, but I do know that this is 100 ohms. Okay, so if you think I'm going to subtract the voltage here, and so that means I'm going to subtract I1 times 100 ohms. And then I keep going. And the second you get back to where you started, you now have a closed loop, and so this is now equal to 0. All right, notice, by the way, I can immediately solve this equation for I1, okay, because I can do some basic algebra and get 3 over 100, which is 0.03 amperes, which means I immediately know I2 because I know they have to add to be 0.18 amperes. Okay, so now I can completely solve this circuit, and it was all by using a combination of the junction rule and the loop rule. Okay, so basically I'm done with this problem. But just to show you how, if this was a more complicated circuit, I could keep making loops and keep getting more equations. Let me show you what that would look like. Okay, so let's say I want to apply the loop rule again. Okay, so let's say I start off in the same location. I make a loop. I go up 3 volts, so I add 3. I keep going, I keep going, I keep going, and let's say I go this way instead. Okay, so now I'm adding the voltage here, and the voltage, the potential difference here is given by V equals I times R, and I'm going down in potential, so I'm going to do minus I2 times 20, and I keep going. As soon as I get back to where I started, it's all over. I'm done. It's equal to 0. And if you solve that, you get I2 equals 3 over 20, which is 0.15 amperes, which is what we found before. Right? And so notice every time you make a different loop, you get a different equation. And in some complicated circuits, you can actually end up with systems of equations. Okay, one of the most common like real life applications of systems of equations is circuit analysis. Okay, so that's the type of thing where if you were doing like electrical engineering, you would learn like linear algebra and how to solve system of equations for that type of situation. Because every time you do the loop rule, you get a different equation. And so if you had a really complicated circuit, you could have like, 5 or 10 or 20 or 100 resistors, and each loop is going to give you a different equation. Okay, we're not going to see anything crazy like that in this class, but just to give you an idea. Okay, but this circuit is so simple, we don't actually have to make multiple loops, but it still works. Okay, so pause there if you want to look at that some more. Now, I do want to point one other thing out to you right now. Okay, so let's say I make a different loop. Let's say I start here, and let's say I go down. Okay, and there's a voltage drop here, and so that would be minus I1 times 100. And let's say I go this way. Whenever you go against the current, so here we're going against the current, you actually go up in potential. And so I'm going to go up V equals I times R. Okay, so that's I2 times 20. And as soon as I get back to where I started, that's equal to 0. Now, if you don't know I1 or I2, that doesn't really help you, but I do want to point something out. Okay, in order for this number and this number to add to be 0, they have to be the same in magnitude. It's just one is positive and one is negative. What I'm telling you is that both of these resistors that we see here have the same voltage. Okay, they have the same potential difference across them. And as we'll see here later on, this is what we call a parallel circuit when you have two or more resistors that have the same potential difference. Okay, so we'll see more of that later. All right, so let's take a look at example 2. All right, and again, we're going to apply Kirchoff's laws. Okay, so here I don't know any of the currents right away, and actually this circuit on the left, there is no junction. There is no place where the current can split. So forget about the junction rule. Let's just go straight to the loop, and um, I'm going to start right here. I always like to start right by the cell. Honestly, it makes no difference where you start. It doesn't really even matter which way you go. I just prefer to go in the same direction as the current. And I know the current's going to go counterclockwise because it's going to come out of the positive side and go around to the negative side. Okay, so I don't know the current in the circuit, but I do know that if I start here and I add up the voltages, I'm going to go up 12 volts across this battery. I keep going, keep going, keep going, keep going. Okay, I'm going to go down some number of volts right here, and that's given by V equals I times R. I don't know what I is, but I know that's 10 ohms, so the resistance there is 10 ohms. So that's minus I times, wow, that's a 10 out of 20, minus I times 10. I keep going with my loop. Notice the current here is the exact same because there is no junction, there's no place for the current to split. Okay, so again, I have minus I times R, and it's the same I, but now R is 5. The second you get back to where you started, the loop rule is done, and it's equal to 0. Okay, so now, even though I didn't know what the current was, I can now find the current because I can combine these like terms. Okay, minus 10 minus 5, that's a minus 15I equals 0. So I is equal to 12 divided by 15, which is, let's see, what is that? 4 over 5, which is 0.8 amperes. Okay, so that gives me a really simple way to solve that basic circuit. Okay, so now I know how much current is going in that circuit. If you take a look at the circuit on the right, we can also apply Kirchoff's laws to this one. Now, here we do have a junction because the current's going to come out here. It's going to hit this junction and it's going to split. Okay, and so just to give these things a name, let's say the current coming out is I1, and let's say the current going up this way is I2, and let's say the current going this way is I3. Then because of the junction rule, I1 has to equal I2 plus I3. All right, well that doesn't help me because I don't know any of those currents. So let's go to the loop rule. Okay, and with the loop rule, you basically just keep making loops until you get something that you can solve. Okay, so I'm going to erase this bit from the last problem. All right, so I'm going to make a loop starting at the top left because I don't know, that's what I feel like doing. And I'm going to go down just like before. I go up 12 volts. There's nothing here for for there to be a voltage drop. And I'm going to go, let's say my first loop, I'm going to go up this way. Okay, when I go across this resistor, there's a voltage drop. V equals I times R, so that would be I2 times R, which is 5. I get back to where I started. I set that equal to 0. All right, now let's make another loop. Okay, this time I'm going to go along the outer loop, so I have plus 12. I go down, V equals I times R. That's minus I3 times 10 equal to 0. So I can find I2 and I3 right away. I2 is going to be, let's see, that'd be 12 divided by 5, which that would be 2.4 amperes. And then I3 is going to be 12 divided by 10, which is 1.2 amperes. which means that the current coming out of the cell, or not out of the cell, out of the battery, the current coming out of the battery is actually 2.4 plus 1.2, which is 3.6 amperes. So I now know how much current is coming out of the battery. The other thing I want to point out is that the current actually splits proportionally. And so this is kind of a conceptual thing, but it's important that you understand that the current I1 comes straight out of the battery, and then it hits the junction. Okay, it hits the junction right here, and it splits proportionally. You might have heard the phrase path of least resistance. Okay, well that kind of comes from current and circuits. So the current is going to hit that junction, and it wants to go where there's less resistance. Okay, if one path has 5 ohms and the other path has 10 ohms, in other words, if one pathway has twice as much resistance, that means half the current is going to go, or the current that goes to the 10 ohm resistor is going to be half of what goes through the 5 ohm resistor. Okay, in other words, 10 is double what 5 is, and so double the resistance means that pathway gets half the current. All right, so it splits proportionally. In other words, if it was 5 ohms and 5 ohms, then it would split like 50-50. Okay, here it doesn't split 50-50, um, but hopefully that makes sense. Now, the next place we're going to lead, we're actually going to stop the video here and then do more examples in the next video. Um, But this type of circuit on the left is what we're going to call a series circuit. And in a series circuit, the current through each component is the same. Okay, here we can see it's series um, because there is no junction anywhere, and so the current going into the 10 ohm is the same as the current going into the 5 ohm resistor. This one on the right side is what we call a parallel circuit. And as we'll see in the next video, the definition of a parallel circuit is one in which both components have the same voltage. Okay, but we'll talk more about that in the next video. Hopefully that made Kirchoff's laws make a little bit more sense, seeing some examples. You also have some worksheet problems to work on to get a little bit more practice. As always, please let me know if you have any questions, and I'll see you guys in the next video.